If you're plugged into the world of network security, you know the job is less about just setting up firewalls and more about managing this endless stream of policies and logs and
Yeah,
protocols.
the sheer volume can be completely overwhelming.
It really can. You need to know how it works, the functional knowledge, not just the textbook definitions.
That's exactly why we structured this deep dive the way we have. We've taken a really focused stack of source material to cut through all that noise.
Okay.
We're not here to just memorize answers to some practice questions. We're here to really extract the operational why behind all these key components.
So today we're doing a kind of rapid fire tour of what's actually happening under the hood. We've got 5 core areas we're going to hit: system troubleshooting, authentication, security profiles, routing, and VPNs.
Right, and our goal is that by the time we're done, you can look at a log message or a design choice and just instantly get what it means on a practical level.
Let's do it. So where do we start?
Let's start at the most critical point in any modern network.
Yeah.
Identity, specifically in a zero-trust world.
Okay, let's unpack this idea of zero trust network access, or ZTNA. It completely moves the security boundary, right? It's not about being on the trusted network anymore.
Not at all. Access is granted because the system trusts who you are and, just as important, the state of your device.
And what's fascinating is how the architecture splits up that job of verification.
It does. You have to verify the device meets a security baseline. Is it patched? Is the antivirus running? And the big question is, who's responsible for collecting all that data and actually generating the access tag?
That brings us to our first major operational point. A lot of people might think the firewall, the FortiGate, does everything. But the component that generates and applies those dynamic tags to the endpoint is actually the FortiClient EMS, the endpoint management server.
That division of labor is absolutely fundamental. If you're troubleshooting ZTNA, you have to get this right. EMS is the intelligence layer. It's on the endpoint. It's collecting that granular posture info and generates the security tag. The FortiGate is just the enforcement point.
So the firewall is the bouncer,
Yeah.
but the EMS is the one checking the ID and making sure you meet the dress code before you even get to the door.
Perfect analogy. The FortiGate receives the tag and enforces the policy, but it never creates that posture tag itself.
That makes a ton of sense for scaling. So we've got the posture check covered with that dynamic tag. But I know ZTNA needs 2 things for a connection. What's the other non-negotiable part?
This is where identity gets really serious. You've proven your device is compliant with the tag, but we still need, strong cryptographic proof of the actual user's identity.
Okay.
And the source material is crystal clear on this. A successful ZTNA connection requires 2 things: that matching security tag for device compliance and a trusted client certificate for identity.
It's that cryptographic proof that ties the person to the policy. So you need both keys to open the door, the compliant device tag, and that trusted client cert.
Absolutely. If you try to connect without that client certificate, even if your laptop is perfectly patched,
You're dead in the water.
you're dead in the water. It turns a simple username and password check into this 3-part verification: compliant device, authenticated user, and cryptographically verified identity. That's modern zero trust.
Okay, let's connect that to something a bit more legacy. A lot of places still use directory services like LDAP for admin logins. What's the single biggest security win you get by using encrypted LDAP, so LDAP PS instead of plain text?
This is just security 101, but it's so critical. The main benefit is that it stops your credentials from being snatched right off the network.
So sniffing attacks.
Exactly. If you're using plain text LDAP, an attacker just needs to sniff packets on the wire. A man-in-the-middle attack, a rogue switch, whatever, and boom, they have your admin username and password in clear text.
It's purely about confidentiality during transit then. Encryption just takes that whole attack vector off the table.
It's the difference between sending your password on a postcard versus in an encrypted email. For admin access to your core infrastructure, only one of those is acceptable.
Okay, so we've established how we verify identity. But what good is that if the security system itself just, collapses?
Right.
Let's pivot to resilience. How do we make sure the fabric doesn't fail? Let's start with high availability. In a standard active-passive setup, what are the 2 specific things that will trigger a failover?
This is a great question because HA is tuned to only react to very specific, very critical failures.
So it's not twitchy.
It's not twitchy at all.
Yeah.
According to the source material, a failover is only triggered by one of 2 things. First, a failure of a monitored network interface link. So a cable gets unplugged, a switch port dies,
A physical disruption.
a physical disruption. Or second, a manual reboot of the primary unit. That's it.
So that tells you what it's designed not to do. It won't fail over for, like, changing an admin password or if the log disk gets a little busy for a minute.
Exactly right. The system can tell the difference between normal operational stress and a catastrophic failure. It's looking for total system unavailability, not temporary hiccups.
Okay, let's move from hardware failure to internal stress. Let's talk about the intrusion prevention system, or IPS. The IPS engine is a memory hog, right?
Huge. It's incredibly resource intensive.
Which leads to this classic trade-off. What happens when the IPS goes into what's called fail-open mode because it's running out of memory?
This is where the choices get really, really stark. When the IPS engine is under that much stress, it has to prioritize. And it prioritizes network availability over security enforcement.
So what does that actually mean for the traffic?
It means the traffic is allowed to pass through the firewall, but, and this is the critical part, it passes through without being inspected.
Wait, so the very expensive inspection engine we bought becomes, what, a basic packet filter for a little while?
For a little while, yes. That's the painful reality of failopen. You temporarily sacrifice that deep security inspection to make sure that business-critical traffic doesn't just stop flowing.
Because a full-on service disruption is often seen as the bigger, more immediate business threat.
Exactly. It's a risk calculation that's baked right into the design. Once memory usage recovers, the IPS engine will kick back in and resume inspection.
It's a controlled failure. Okay, let's pivot from that internal stress to an external attack, specifically during VPN setup IKv2 negotiation. How do we stop an attacker from just overwhelming our gateway? What's the purpose of the IKv2 cookie challenge?
The cookie challenge is a purely defensive mechanism. It's there to stop denial of service or DOS attacks.
Because the negotiations themselves take up resources.
A lot of resources. CPU, memory, state tracking. An attacker could send thousands of spoofed IKE requests and just exhaust the gateway.
And what does the cookie challenge physically do to stop that?
It's basically a very lightweight initial handshake. The VPN gateway gets a request, and instead of spinning up all its resources, it just sends a little cryptographic cookie back to the source address.
Okay.
The initiator has to send that same cookie back to prove it's really at that address. Only after the gateway verifies the cookie does it dedicate the heavy resources to building the actual VPN tunnel. It's a way to filter out the fakes before you waste your energy.
We've covered identity and resilience. Now let's get into traffic flow. When things break, you need to know what you're looking at. So you're running a debug flow, and you see the message, denied by forward policy. What does that tell you instantly?
This one debug message can save you hours. Denied by forward policy means one thing and one thing only. The packet was dropped because the traffic did not match any active firewall policy.
So it hit the implicit deny all rule at the very bottom.
It hit the implicit deny. That's it.
Which means I can immediately stop checking my routing table. It's not a routing problem.
Correct. The packet got to the firewall just fine.
And it's not a problem with a security profile like IPS because the policy check happens before any of that. The problem is purely in the firewall policy itself.
Precisely. The firewall looked at the source destination service, and it found no explicit allow rule. So your entire focus should be on the policy matrix, nothing else.
Let's talk security profiles again, this time SSL deep inspection. This is when the help desk phone starts ringing off the hook, right? Users start seeing certificate warnings everywhere. Why does that warning pop up?
The problem is all about trust, or a lack of trust. During deep inspection, the firewall basically performs a man-in-the-middle on the traffic.
Right.
It intercepts the real server certificate and then resigns a copy of it using its own internal certificate authority, its own CA.
And the user's browser sees that and freaks out.
It freaks out because the client device, the browser, the phone, does not trust the firewall's CA certificate. It sees the signature from some unknown internal appliance, not a globally trusted one like Let's Encrypt or DigiCert, and it flags the connection as suspicious.
So to make this work seamlessly, you have to push that firewall's CA certificate out to every single client device on the network so they'll trust it.
That's the only way.
Okay, let's move into modern routing with SD-WAN. The whole point is to dynamically pick the best link for an application. What are the two key performance metrics that SD-WAN health checks are constantly looking at?
It's all about optimizing the user's application experience, which means you care about speed and consistency. So the two essential metrics are packet latency and packet jitter.
Latency is just delay, how long it takes to get there.
Right, and jitter is the variation in that delay.
And for real-time stuff like a voice call or a video conference, jitter is the real killer, isn't it? I'd almost rather have a high but consistent latency than a connection that's all over the place.
Oh, absolutely. High jitter is what gives you that choppy audio and frozen video.
Right.
It's maddening. SD-WAN is designed to monitor both of those metrics constantly, so it can shift traffic away from a link that's getting congested or failing.
Okay, last one. Let's look at large-scale mesh VPNs, specifically AD-VPN. The goal here is efficiency, right? Letting branch offices talk directly to each other without bogging down the main hub.
Exactly. You want to escape that classic hub-and-spoke bottleneck.
So for two spokes to find each other and build one of those direct tunnels, what two things are absolutely necessary?
To get that full mesh connectivity, you need two components working together. First, you need a dynamic routing protocol running over the VPN, usually BGP or OSPF.
Okay, and that lets the spokes learn the routes to each other through the hub initially.
Right. The hub acts as the route reflector. So spoke A learns, hey, I know how to get to spoke B, and the next hop is the hub.
But just knowing the route isn't enough to build the direct tunnel.
Correct. That's the second piece. You need shortcut extensions enabled in the VPN settings. Once traffic starts to flow from A to B through the hub, these extensions signal that a direct spoke-to-spoke tunnel should be built.
So dynamic routing tells them where to go.
And the shortcuts actually build the direct road to get there on demand.
Given that these network devices, as we've seen, often prioritize service uptime over security inspection when they face resource constraints, how should your organization define its acceptable level of risk for these temporary security gaps versus a full-on service disruption? When does security always win, no matter the cost to uptime? And when does availability have to take priority just to keep the business running? It's a policy decision that has to be built on these technical facts.